Continuing with our understanding of operations and procedures at the data link layer, we are also interested in understanding the performance of the medium access sublayer of the data link layer. The medium access control sublayer is responsible for the successful access of the channel so that the data could be delivered by various users. We are interested in determining how much throughput could be achieved. For that, we'd start with the understanding of an ideal MAC channel. We'd look at the issues which arise in a more practical network, and then we'll conclude with representations which are used in the real world. A very relevant reference by Hachol Lee, a MAC throughput in the wireless LAN, is included for your reference, along with the textbook by Kuros and Ross. Let's look at the ideal MAC first. In an ideal MAC, which is of course hypothetical, if the channel has the total capacity of capital R bits per second, if there were only one node which is active, it should be able to utilize all these R bits. If the number of nodes increase up to M, since it's an ideal channel, so the uniform or fair distribution of this R should be taking place such that each of these senders is taking R divided by M share. This requires that there is a fully decentralized mechanism which is not offering any redundancy whatsoever. There is no server that is coordinating the transmissions between multiple senders, and there is no overhead of this special node. There is no centralized clock, because a clock means that each node will have to wait for the clock interval to start, and there are no slots. And most important of all, this is a simple MAC scheme. In reality, none of these is true, because if we were to make such a protocol that achieves all these functionalities, we would be able to utilize 100% of the available bandwidth. But we see that although Shannon's capacity theorem provides upper bounds on the channel utilization, no real-world system has been able to approach that so far. In real world, the channel access is not exactly always direct and always certain. Let's look at a wired scenario first. Here, this timeline or the overall time interval is shown to be split into various epochs, or we say various phases. For example, there could be a time which is actually the useful time when the channel is being utilized in terms of data transmission, when multiple sources are just competing and fighting over who gets to send data is the busy channel time. Then after the busy channel time, we have some kind of silence interval, that is carrier sensing or collision detection interval. Then there is absolute silence when none of these users is active in terms of ideal slots. Then we also see that we have after data delivery short interframe spacing, and after acknowledgement we have the distributed interframe spacing. So the overall time is now split into useful time and useless time. And this is what we see in wired scenario. The problem is even aggravated in wireless scenarios. Strategies such as wireless Aloha, for instance, when we look at the RTS, CTS based protocols, we see that the overall time is now split into additional functionalities. For instance, the request to send time is taken by the messages which are carrying the requests, the clear to send time, which is the time involved in acknowledgements of RTSs, and the other times that we've seen before. Here, the handshaking process is taking its toll on the overall data rate availability. So we say that the throughput of MAC is highly dependent, is affected by various factors. For example, what protocol is being used, what is the number of active users, what is the total number of users, how much resources are being provisioned, how much traffic is coming from every user. In certainty, we say that it is a probabilistic behavior that depends and affects the throughput of medium access control sublayer.